Okay, Module 15 study guide. First, let's take a look at these top 4 problems. It says find the common ratio, R, for each geometric sequence, and use R to find the next 3 terms. So this is a geometric sequence. How can we tell? Well, it looks like we're multiplying by a common ratio. Okay, now what is that common ratio? To find that common ratio, you could just take any of these terms and divide it by the previous term. This one's pretty easy. This one's pretty simple to figure out. It's obvious that we're multiplying by 3 each time. But if you didn't see that, then all you would have to do is take one of your terms, divide it by your previous. That would give you 3, and that is your common ratio. So your common ratio is 3, which means that we're multiplying by 3 each time. So 135 times 3 would give me my next term, which is 405. 405 times 3 would give me my next term, which is 1,215. And 1,215 times 3 would give me my next and final term, which is 3,645. All right, so next, again, you could just take one of your terms and divide it by your previous term. 6 divided by -2 would give you -3, which is our common ratio. We're multiplying by -3 every time. So 54 times -3, if we're continuing this for the next 3 terms, that would be -162. If we multiply that by 3, we'd get 486. And if we multiply that by -3, I think I left negative out last time, but it is -3. It'd be 1,458. So next we have 200, -80, 32, -12.8. So my common ratio is going to be negative again. Just take your term here and divide it by the previous. Doesn't matter which one you choose. So -80 divided by 200 would give me my common ratio, which is -0.4. We're multiplying by -4/10 every time. So our next 3 terms would be 5.12. -2.048 and 0.8192. And last, number 4. So we have 5, 3, 1.8. So 3, we take our term divided by the previous, which would just be 3/5, which 3/5 as a decimal would be 0.6. Our common ratio would be 0.6. Our next 3 terms, if we're multiplying each time by 0.6, would be 0.648, 0.3888, and 0.23328. All right, again, I forgot to mention this when we started this, but please, if you can, try to do these on your own. And don't just watch me give you the answers. Just try to do them on your own and then just use this video to check your work. So biologists studying ants started on day 1 with a population of 1,500 ants, 1,500 ants. Day 2, there were 3,000 ants. Day 3, there were 6,000 ants. So this is a geometric sequence. We want to know what the population is going to be on day 5. So day 1, which would be our first term, that would be 1,500. Day 2 would be 3,000. Day 3 would be 6,000. So this one, it's pretty obvious that we're multiplying by 2 each time, but you could take your 3,000 and divide it by 1,500, and that would give you your common ratio, which is 2. And we could go ahead and write we could write an explicit rule and figure out the 5th term like that, or we could just continue this. So our 4th day, if 6,000 was our 3rd day, to find our 4th day, we'd have to multiply by 2. So that would be 12,000. And we'd multiply by 2 one more time to find the 5th day, and that would give us our answer, which is 24,000 ants on the 5th day. Again, you could have also created an explicit rule and done it that way. I think it's just as easy to just go ahead and continue this. So you need to remember how to write an explicit rule for a geometric sequence and how to write a recursive rule for a geometric sequence, right? If you don't remember it, Write this down all over your notes. Write it down 20 times if you need to, but you need to remember, for explicit, it's going to be f of n equals f of 1 times your common ratio raised to the n minus 1 power. That's for explicit. For recursive, so given f of 1, it's going to be f of n equals f of n minus 1, which remember f of n minus 1 just means previous term, times your common ratio. And that's for any n that's greater than or equal to 2. Okay, so you need to remember both of these for tomorrow. And you'll need them for the study guide as well, because we're going to do that. We're going to use these for 6. 6, it says write a geometric sequence and a recursive sequence for each of these. Write an explicit rule and a recursive rule for each of these geometric sequences. So here, if you find your common ratio, you'll see that the common ratio for this problem, is we're multiplying by 1/2 is 0.5. So the common ratio is 0.5. So our first term is 10. So for writing an explicit, it's going to be, remember, it's f of n equals your first term, which is 10, times the common ratio, which is 0.5, raised to the n minus 1 power. Okay? And that's all you would have to do. For recursive, it would be f of n equals f of n minus 1 times your common ratio, which is 1/2 or 0.5. Okay? And this is for any n that's greater than or equal to 2, and we're given our first term, which is right over here. Explicit. So first, what is our common ratio? It looks like we are multiplying once again by 0.5, but this time it's negative 0.5. So our common ratio would be negative 0.5. So for explicit, and our first term is going to be negative 12. So for explicit, it's going to be f of n equals your first term, which is negative 12, times your common ratio, negative 0.5, raised to the n minus 1 power. That's all you would have to do with these kind of problems. For recursive, it would be f of n equals f of n minus 1, which means previous term, times your common ratio, which is negative 0.5. And that's for any n that's greater than or equal to 2. Here we have an exponential function, and we are asked to complete the table and then graph the function. Okay, so let's go ahead and draw a table. And they're giving us specific terms that they want us to use. So this isn't going to be a continuous exponential function. There's going to be a discrete exponential function, which just means we're not going to connect them. They didn't give us specific domain values, and they just told us to graph it. Then we would connect it with a curved line. So right here at 0, that's going to be our starting point. Remember, the exponential formula is y equals a times bx, where a, which in this case would be 1/2, is your starting point. It's where we cross the y-axis. So we could already put in 1/2 right there where 0 is, because that's going to be our starting point. B is a multiplier. It just tells us whether it's going to be a exponential growth or it's going to be an exponential decay. So because the B is 4, it's going to be an exponential growth. So our multiplier is 4. That means we're multiplying by 4 every time. So if we know that 0 is 1/2, to get to 1, we'd have to multiply by 4. 1/2 times 4 would be 2. Okay? And then to get to our second domain value, we'd have to multiply by 4 again, which would be 8. If we want to go backwards to figure out what the range would be at -1, instead of multiplying by 4, we'd have to divide by 4, which would be 1/8. And then to find what the range would be when the domain is -2, we'd have to divide by 4 again, which would be 1/32. And then we'll go ahead and plot these points on the coordinate plane. And that's what it would look like. Now notice I did not connect these with a curve or a line or anything, because they gave us a specific domain value we need to stick with that specific domain value. We have our range. We just leave it as a discrete. We're not going to connect it. We're just going to plot the points on a coordinate plane. Write an equation for the function that includes these 2 points. Luckily, they're consecutive points, 2 and 3. So remember the formula for exponential is y equals a times b to the x power, where b is your common ratio, it's your multiplier. We know how to find our common ratio. We take one term and multiply it by the previous term. And luckily, we have the previous term because this is term 3 here and this is term 2 here. So the previous term, if we're in term 3, would be term 2. And if we divide 1,000 by 100, we find our common multiplier, our common ratio, which is 10. All right. Here's the thing, though. We also need a. We also need our f of 0. We need our y-intercept. We need our starting point. Okay. How do we figure out a? Well, we know that this right here is one of my points. 2, 100 is one of my points. So what I could do is I could go ahead and plug 2, 100 into this formula, and that'll help me find a. Here's what I mean by that. So the ordered pair again is 2, 100, which y represents 100 and x represents 2. So I'm just substituting those into my exponential formula. So it'd be 100 equals a. We don't know a yet. That's what we're trying to solve for. That's what we're trying to figure out. Times b. Well, we know what b is. B is 10, so I can fill that out. Raised to the x power. Well, we know what x is too. X is 2. We know what x is 2, which is TOO, and then x is the number 2. So we're raising that to the second power. Okay? So that means 100 equals a times 100, and then we would divide by 100 on both sides. A is going to equal 1. And there we have it. So we can go ahead and write our exponential function, which would be y equals 1 times bx, or just bx. So it would just be 10 to the x power. Y equals 10 to the x power. State a, b in the y-intercept, then graph the function and describe the end behavior. Also, I'm going to want you to state the asymptote. So remember, it's y equals a, b, x. So the numbers in the a position is 9, which that would mean that 9, because we're not shifting over by anything, is going to be our y-intercept. So our y-intercept, we could already answer that question, is 0, 9, right? B is our multiplier. On your test tomorrow, I'm going to ask you whether that's going to be a exponential growth or exponential decay. Because our multiplier is greater than 1, it's going to be a growth. Okay? Let's see, what else are they asking us for? B, we identified that. We also identified that it's a growth. Y-intercept, we did that. Now, where would the asymptote be? We could already answer that one without graphing it either. So because we're not shifting, because we don't have plus or minus anything on the right-hand side of this exponential function, that means our asymptote is going to be at y equals 0. And remember what asymptote means. So asymptote is where the line drags off. It gets closer and closer to that asymptote, but it never touches it. Okay? And review those definitions on your notes. Review those videos from yesterday and the day before yesterday if you need to. Now, we're going to go ahead and graph this using a table. So remember, a was 9, so we'll put 9 here in the middle, and that is our y-intercept, so we know that x is going to be 0. What's our multiplier? Our multiplier is 3, right? So that means we're multiplying by 3 every time. Remember, b is what multiplier is, so in this right here, in this exponential function, b was 3, so that's our multiplier. That's what we're multiplying by every time in this geometric sequence. So if we multiply 9 by 3, our first term would be 27. We multiply by 3 again, we get 81. If we want to go backwards, we divide by 3, we get 3 for negative 1. Okay? We divide by 3 again, we get 1 for negative 2. So our ordered pairs would be negative 2, 1, negative 1, 3, 0, 9, 1, 27, and 2 comma 81. Okay? This time they didn't give a specific set of domain values, so we are going to connect this when we graph it. And you're going to see that our asymptote is in fact y equals 0. So go ahead and pause the video and graph these ordered pairs. And there you have it. And you can see as this exponential function approaches negative infinity on the x-axis, as our domain approaches negative infinity, the function gets closer and closer and closer to 0, but it's never going to touch 0. Okay? So what would the domain be for this? Just a side question here. What would the domain be? Your domain's going to be all reals, right? And we discussed that in class. What would your range be? Well, your asymptote is at 0, right? And what is the graph doing at 0? Is it above 0 or below 0? It's above 0, so it's going to be y is greater than 0. Not greater than or equal to. We're not including 0 because it's never actually going to touch 0. So now we have y is equal to 1/3 x plus 4. So remember, the exponential formula, the exponential equation is y equals a times b raised to the x power. Doesn't really look like we have something in the a value, but when it doesn't seem apparent what our a is, then that means we probably have 1 for a. There's an invisible 1 there, if you will. So a is actually going to be 1, right? And I hope that makes sense, because 1 times 1/3 raised to the x power would still be 1/3 of the x power. Okay, so a would in fact be 1. What would b? B is going to be 1/3. Okay, and that right there tells us that this is going to be a decay. I'll put that in parentheses because our multiplier b is less than 1. It's a fraction. All right, this time we have a plus 4 here, which is going to shift the graph up 4 spaces. Okay, so keep that in mind when we graph this and when we find our table in just a moment. All right, so first let's find our, let's go ahead and do our table. So in class I told you that it might be easier just to first do a table for y equals 1/3 x without the shift, and then do another table where we just shift all of our values up 4. So if we just do a table for y equals 1/3 x, we know that our starting point would be 1, okay, because our a would be 1. All right, and what are we doing each time? We are multiplying by 1/3. So 1 times 1/3 would be 1/3. If we get another point, 2 times 1/3 times 1/3 would be 1/9. All right, and if we're going backwards, that means we're going to be dividing by 1/3. So 1 divided by 1/3 is 3. If we divide by 1/3 again, 3 divided by 1/3 is 9. Now this would need to be shifted up 4 spaces because we had a shift right here. This shifted it up 4 spaces. So what I'm going to do is I'm going to take all those values that we just came up with and I'm going to add 4 to them. So at 0 instead of at 1, we're going to be at 5. At 1 instead of 1/3, we're going to be at 4 1/3. At 2 instead of at 1/9, we're going to be at 4 1/9. Right? Because we're just adding 4 every time. At -1 instead of 3, we're going to be at, if we add 4, we're going to be at 7. At -2 instead of 9, we're going to be at 13 if we add 4. Okay, so these would be your new points. Now before we graph this, go ahead and think about what I told you in class. Think about where our asymptote would be. I told you if we didn't have any shifts, our asymptote is going to be at y equals 0. But if we did have a shift, our asymptote is just going to be whatever that shift value is. So in this case, our shift value is 4. So our asymptote is going to be 4. Our asymptote is going to be 4. I hope you remember that from class yesterday, or today, I'm sorry. Or maybe yesterday, depending on when you're watching this video. So go ahead and graph these points, and this should be an exponential decay, so let's see what this exponential function does when we graph it. And there you have it. So you can see that this line is a decay, and you can see that the line is approaching, as we're going towards positive infinity on our x-axis, on our domain, it's approaching that y equals 4 line, but it never actually touches it. That's our asymptote, okay? What would the domain be? domain would be all reals. What would the range be? The range would be, well, 4 is our asymptote, and what's happening at our asymptote looks like y is going to be greater than 4. Not including 4, but just greater than 4 would be our range. Okay, and I think I answered all the questions that it told us to answer, so that's it. A couple more, and we're going to do these quickly. So here we have 0.4 raised to the x power, and here we have 0.4 raised to the x power plus 5. So what's happening? We're shifting up by 5. So g of x is shifting up by 5. All right? And here we have negative 2 times 1.5 raised to the x power, and then the second function is a negative 2 times 1.5 raised to the x power minus 2. So this one we are going to shift down 2 spaces, 2 units, because it's a minus 2. Okay, that's it. I think this video was pretty shorter than my usual study guide video, so there you have it. Study for this, study your notes, get ready for this. I want everyone to pass this test tomorrow, and I know you guys are able to, so I will see you tomorrow. Good luck. Have a great night.